So we are given, so this is like a multivariable calculus optimization problem. We are given that when X nuts are produced, they can be sold for negative 3X plus $500 each. And when Y bolts are produced, they can be sold for negative Y plus $300 each. Also, if there's a little pop-up blocking my face about Google Chrome, that is a glitch that Wyzant is experiencing, and I've put in a support request, and I've tried everything, and there's nothing I can do about it. So sorry if my face is being blocked. It shouldn't affect our math here. Okay. So we are concerned with revenue, though, and that's kind of the trick to this, to setting it up, is that, okay, if we produce X nuts, for one thing, we have to assume we sell every nut we produce. There's nothing we can do about that. So we have to make that assumption. So the revenue from our nuts is, okay, however many we produce, which is X, times however many times how much we can sell them for. And let's just go ahead and clean that up now because we know we're going to have to anyway. So algebra, that's negative 3x squared plus 500x. And then do the same thing with our bolts. So the revenue from our bolts is going to be y times, right? We produced y bolts, and we can sell them for negative y plus 300. Which cleans up to negative y squared plus 300y. Okay, so that is going to be our revenue equation. Our total revenue now is we're adding together our revenue from our nuts and our revenue from our bolts. So that's a function of two variables, so I'm going to call it that. I'm going to call it, we could call it R if we wanted, but I'm just going to call it F just so we can stick with like the lingo of, spoiler alert, we're going to use something called Lagrange multipliers for this. We kind of have to use those for this. So hopefully you went over those in class. If not, I'll just kind of show you how they work. So our revenue is those two things added together. And I'm going to pretty it up a little bit. I'm going to call it, okay, negative 3x squared minus y squared plus 500x plus 300y. Okay, so we have to maximize that revenue. However, that's like a big curvy parabolic type shape in the 3D plane, and there really is no maximum value for it. But fortunately, we have a constraint. So that's what we need. So assume that nuts and bolts weigh 0.5 kilograms each, and we want to make 100 kilograms of steel. So that means that, so all this is our like weight equation. So we have an equation for revenue, and now we have an equation for weight. And we know that, okay, our total nuts are going to weigh 0.5 times however many nuts we make. Our total bolts, I'm sorry, these little decimals are so small, are going to weigh 0.5 times however many bolts we make. And we know that that has to equal 100 kilograms. And it's actually going to make our life a little easier. There's really no reason not to rewrite this equation. We have a 0.5 on this side here, so let's just get rid of it. Let's multiply both sides by 2 and just make that equation simpler and just change that into x plus y equals 200. Right, this is a linear equation in x and y. There's no reason we can't do that. Okay, so that becomes our constraint equation becomes our g of x, y. So g of x comma y equals x plus y. And we know that that has to equal 200. So again, hopefully you went over Lagrange multipliers in class. I'm not going to prove how they work or like explain how they work really. I'm just going to say they work and here's how to use them. If you don't care how they work, then fine, just follow along with me. I want you to care though. Okay, so we have, so let me pop up to a new thing and just summarize everything we have here. We have the f of x comma y is negative 3x squared minus y squared plus 500x plus 300y. All right. So that function itself has no maximum, but since we have a constraint, it does. So our g of xy equals x plus y, and we know that that has to equal 200. So really what we're doing here, this is a big parabola type of shape. You can't see where I'm pointing, I don't think. This is a parabola. This is a plane. We are finding the intersection. Just picture in your head the intersection of a parabola and a plane. They're going to intersect in like an ellipse, like a kind of tilted ellipse. And then the ellipse has a highest point. So if we could graph this, the graph is ugly because these numbers are so big. I'll try to show it to you. But whatever. That's what we would be looking for visually. So algebraically, here's what happens. So again, hopefully you've done this before. We calculate f of x and we look for a special value of this number lambda, where f of x, sorry, not f of x, the derivative of f with respect to x, the partial derivative, right, is lambda times the derivative of g with respect to x. And the same thing with y. The derivative of f with respect to y is the same thing as lambda times the derivative of g with respect to y. Okay, so that gives us two equations, and then this, the constraint, gives us our third equation. So we essentially have a couple equations and a couple of variables, and that's a system that we can solve. And there's no real one way to do that. Sometimes it takes a little bit of creativity. This one's not that bad, but the way you do it at home might be a little different than the way I do it and still work out just fine. Okay, so it's just the way I figured it out. Okay, so these actual partial derivatives are super easy. So the partial derivative of f with respect to x is, okay, so that's just a straight up partial. It's negative 6x plus 500, right? What did I just say? Negative 6x plus 500. And let's just do them all. The partial derivative of g with respect to x, well, look at g. It's just x plus y, so that's just 1. Okay, do the same thing for y. The partial derivative of f with respect to y is negative 2y plus 300, right? This is kind of Calc 1 type stuff. This is for Calc 3. This is pretty easy. And gy, the same thing as 1. And then we just have our third equation is going to be just that x plus y equals 200. Okay, going to a new board. So here's our system of three equations. It's negative 6x plus 500 equals lambda times just 1, right? I'll put the times 1 just so you know that that is in there. And then we have negative 2y plus 300 once again equals lambda times just 1. And then so that's two equations. We still have a lambda in here. We'll figure out what lambda has to be. Or we actually don't have to figure out what lambda has to be to solve this problem. And then we have our third equation, which is x plus y equals 200 from our constraint. Okay, so here's the way I'm going to do it. Again, you could pause the video now and maybe try and figure out how to solve this for x and y yourself. In fact, I would kind of encourage you to do that, especially if you've already done a problem like this in class, because ultimately it's up to you. So as a teacher, I'm encouraging you to finish this part yourself. So I'm going to do it anyways, though. So you're going to pause the video and try it yourself. Okay. In 3, 2, 1, pause. Now I'm going to go ahead and finish it anyways. And, you know, if you finish the video, fast forward to the end here, or if you finish the problem, fast forward to the end and make sure we got the same thing. Okay. So here's how I'm going to do it. I'm going to say 6x plus 500 equals lambda. And also negative 2y plus 300 equals lambda. So let's just set those things equal to each other. Negative 6x plus 500 equals negative 2y plus 300. All right. So that's still an equation with two variables in it, but I can use essentially, remember the substitution method from way back in algebra class. I'm going to take this relationship x plus y equals 200 and solve it for, you could solve it for x or y. So I'm going to solve it for y. I'm going to take this, that's going to go there, and I'm going to say y is 200 minus x. And I'm going to substitute that in there. So I have negative 6x plus 500. So these can take a little bit of creativity. Is negative 2 times, all right, here comes my sub, 200 minus x plus 300. Right, and now, what do we got? We got an equation in one variable, just an x, okay? So solve that sucker for x, and you're done. Okay, so let's see. Let's clean that up. That's negative 400 plus 2x plus 300, which is negative 400 plus 300 is minus 100. So that's 2x minus 100. So let's see, move some stuff around. That's going to give us 8x equals 600. Hopefully I'm not going too fast with my algebra here, which means that x is 600 over 8. Calculator. 600 over 8 is 75. Ta-da! Okay. The only, I mean, you could check this with the graph, but like I said, the graph's kind of hard to look at because these numbers are so big. So, but I can kind of show you. I'll try. Anyways, okay. So that's 75. And now to find y is like, you can do that in your head. So we just have, we know that x plus y is 200. So 75 plus y is 200. And y is 125. And then what are we being asked? So all we were asked is how many nuts and how many bolts. So we'd actually be done. X is 75, y is 125. I always tell my students, I like to know what the actual maximum revenue is. And this is actually the point you'll see on the graph. So you'll want to use a calculator for this. So we're going to plug 75 and 125 back into our original f, that thing with a negative 3x squared minus y squared and stuff. For one thing, this better be a positive number, right? Or else our revenue is negative, and there we go, out of business. So I got, so again, calculator, I got 42,500. So that's the actual revenue from the sale of 75 nuts and 125 bolts. Okay, so you can stop here. I've never done this, but I'm going to try to share my screen with you. Let's see what happens. Aha, Chrome tab. No, window. Okay. Let's see what happens here. Oh, there you go. Hopefully you can see that. So this is the plane that x plus y equals 200. And again, you can't really see the parabola because our numbers are just too big, but I plotted the point. So this is 75 nuts, 120 bolts, and that's the maximum revenue. So one thing that's nice is you can just see that it does in fact sit on that plane. And you'd have to zoom around a lot, but you just have to take my word. There's a very skinny parabola that hits here. Again, it'd just be a kind of a pain to zoom in on just because the numbers are weird. So sometimes you can check these graphically. Sometimes you sort of can't. Okay, so there you go. That's your answer. Multivariable calculus optimization using Lagrange multipliers. Again, if you can't see my face, here I am. That's Wyzant's fault, not my fault. Thank you.